So in the last video, we introduced the spring mass system, and we assumed there's no friction in the spring. So we had x of t defined to be the position of the mass measured from equilibrium. Then we wrote down Newton's second law, mx prime prime equals the sum of the forces, the net force on the mass. And we only put one thing here. We only put one force, which is the force given by Hooke's law, the restoring force of the spring. If you have multiple forces, then the way Newton's second law works is that you add up the forces and you get the so-called net force. So now I'm going to introduce a second force, and that's a damping force. There's some friction in the spring. Okay, so we still have Hooke's law, so we still have the minus kx term on the right-hand side of our differential equation. This was our differential equation from last time. But now we're going to have an additional term having to do with the damping. So let's see, let's create a new page here. So for the damping, it's going to have more to do with x prime rather than x. So it's going to have more to do with how fast and in what direction the spring is moving rather than where it is. So like if I just show you, here, I was showing you a couple of pictures back here. One where the spring is compressed, one where the spring is stretched. And I could tell you in each case how the restoring force should behave, right? Now that doesn't make sense for damping. If the spring is compressed, how should the damping force behave? I don't know. It really depends on how fast the thing is moving. So let me make two pictures like this. Hopefully this will make sense. So I don't care how much this is outstretched, and I don't care where the equilibrium even is. What I care about is the velocity of this thing. So let's say it's moving. How do I indicate that it's moving to the left? How about some motion blur? Like that. It's moving that way. So this is x prime. It's moving that way. And in this situation, some motion blur like this. It's moving that way. If it's moving to the left, then damping is going to be a force that fights against the velocity, basically. So it's going to accelerate it to the right. So if the mass is moving to the left, then damping accelerates it to the right. So damping force will be that way. And if the mass is moving to the right, then damping will accelerate it to the left. In other words, it decelerates it. You might call that deceleration. Acceleration that's against the direction of the motion. And we're going to assume like the simplest model you can have, besides no damping at all, which is damping proportional to the velocity. This is an extreme oversimplification, and that is fine. So I'm going to use gamma for the proportionality constant, and I'm going to say the damping force is this much, proportional to the velocity. Okay, but what should it be, positive or negative? So all these quantities are signed. Should it be positive or negative? Well, in this picture, x prime is negative, and I would like the damping force to be to the right, and I have decided that, I decided very early on that to the right in my picture is positive. So, assuming gamma is positive, and x prime is negative, like it appears to be in this picture, motion is to the left, gamma times x prime will be negative, which is wrong. I want it to be positive so that the damping force is to the right. So I should put a minus sign. And same reasoning here. I should put a minus sign. Why? Because x prime is positive. I'd like my constants to be always positive, so gamma is positive. X prime is positive, so this is positive. That's not what I want. I want it to be negative so that it is going to the left. Okay, so I'm just trying to convince you that no matter which way x prime is going, putting minus gamma x prime as the damping term in our net force is going to be the correct sign. It's going to have the correct sign. Okay, so this was our Newton's second law. Mx prime prime equals the sum of the forces. And what is the sum of the forces? Well, there's what we had from Hooke's law, where K is the spring stiffness. And then there's what we had from damping here. So we're introducing this new term. So our previous differential equation just didn't have this. Now we have this. Here's another way to write this. You can write it like that. Something times x prime prime plus something times x prime plus something times x equals 0. And all of the somethings are constants. So this is the differential equation that we have run into. It involves x prime prime, it involves x prime, it involves x. It could have involved t for a second order differential equation, but it does not involve t, at least not explicitly. Of course, these are functions of time, so time is implicitly there, but not explicitly. So it could have involved t, but it doesn't. And these are all constants. And we're assuming they're positive constants. So mass, positive. This damping coefficient, I assumed it was positive for the sake of determining what sign to make this to put here. And spring constant, I assumed it was positive back in the previous video when I was deciding what sign to put here. And they are constants, so they could have involved time. They could have depended on time, but they turned out not to. So in the previous video, we did a bunch of random guessing to, or not random, not totally random, but we did some guessing to try to solve. Now I'm not going to do that. I'm going to wait until we have our techniques in place, which we will do in the next lecture, probably on Monday. But I just wanted to introduce the differential equation, and I want you to pay attention to the form. Constant times x prime prime plus constant times x prime plus constant times x equals 0. Here's another way of describing it. While not paying attention to, let's describe it while not paying attention to the physical setup that we started with. So pure math. Constant, let's call it a times x prime prime plus constant times x prime plus constant times x equals 0. This is a type of differential equation that we are going to study. These are called second order linear homogeneous differential equations with constant coefficients. And in general, these constants don't need to be positive. Okay, so I'm going to go through all of those adjectives soon, but first I want to show you a second situation where you get exactly the same form. So I'll show you that in the next video.